In the late 1700s, improvements in telescopes allowed astronomers to explore the universe like never before. With these new tools, they began to realize that the universe was far larger than they had imagined. The Milky Way galaxy, which once seemed to be the entire universe, was only one of many galaxies. However, their equipment was limited, and they had no idea that vast regions of space were practically empty of galaxies. The universe remained a largely unexplored mystery at this time. By the early 1900s, advancements in telescope technology and techniques helped astronomers push beyond the Milky Way. They discovered that our galaxy was just one among billions, and the galaxies were not scattered randomly across space. Instead, they tended to clump together in clusters, leaving large regions of space nearly devoid of galaxies. These empty spaces were unusual and seemed like holes in the cosmic fabric, though scientists weren't sure what that meant at first. During the 1970s and 80s, astronomers developed new methods like redshift to measure distances in galaxies. This revealed that galaxies were arranged in patterns, forming a vast cosmic web. Within this web, large voids of empty space appeared, not as gaps in observation, but as real structures in the universe, what we now know as cosmic voids. The Boötes Void is one of the most intriguing mysteries of the universe. It's known as the emptiest region in the cosmos and challenges everything we know about the distribution of matter. This region, located near the constellation Boötes, is vast, with an astonishing diameter of approximately 250 million light-years. To put this into perspective, it's so large that our Milky Way galaxy, along with its neighboring Andromeda galaxy, could fit inside with plenty of room to spare. Despite its immense size, the Boötes Void contains only about 60 galaxies, an incredibly small number when compared to the thousands that would normally occupy such a space. This raises fascinating questions about why this region is so empty and what might have caused such an unusual distribution of matter. The term void might suggest absolute emptiness, but that's not entirely accurate. While this region lacks the dense clusters of galaxies found elsewhere in the universe, it's not a complete vacuum. The galaxies that do exist within the Boötes Void are scattered and isolated, unlike the typical galaxies found in dense clusters or groups. These solitary galaxies stand in stark contrast to the usual behavior of galaxies, which often form gravitationally bound systems with other galaxies. At the edges of the void, galaxies cluster more densely, resembling the cosmic web of interconnected structures that make up the universe. However, within the void itself, the galaxies seem to exist in isolation, as if they were abandoned by their cosmic neighbors. The discovery of the Boötes Void in 1981 by astronomers Robert Kishner, Paul Schechter, Augustus Oemler Jr., and Stephen Schectum added to the mystery. While mapping the universe using galactic redshifts, they noticed an unexpectedly blank region where thousands of galaxies should have been present. Galactic redshifts are a key tool for measuring the distance and motion of galaxies. When a galaxy moves away from us, its light shifts towards the red end of the spectrum, a phenomenon caused by the Doppler effect. Similarly, if a galaxy moves closer, its light shifts towards blue. This effect helps astronomers determine not only how far away a galaxy is, but how fast it's moving relative to us. Using this technique, Kirshner and his team created a three-dimensional map of the universe, and the Boötes Void stood out as an enormous, almost empty region. Further studies revealed some surprising details about the void. Unlike most regions of the universe, where galaxies form dense clusters connected by filaments of dark matter, the Boötes Void is sparsely populated. In fact, the galaxies found within it are so spread out that if you lived on a planet in one of these galaxies, it might take you over 1 billion years to detect the light from your nearest galactic neighbor. This isolation makes the Boötes Void one of the most extreme examples of cosmic emptiness known to science. The size of the Boötes Void is particularly significant. Its diameter spans about 250 million light-years, making it one of the largest voids ever discovered. This means it occupies about 2% of the observable universe's diameter. Despite its size, the number of galaxies it contains is shockingly low. In a region this large, scientists would expect to find at least 2,000 galaxies based on the average density of the universe. Instead, they found just 60, most of which are small and faint, unlike the larger, more luminous galaxies that dominate other parts of the cosmos. The structure of the Boötes Void also adds to its uniqueness. The galaxies within it appear to form a rough, tubular shape running through the center, suggesting that the void might have been formed from the merging of smaller voids. This idea fits with the current understanding of cosmic evolution, where quantum fluctuations in the early universe led to the uneven distribution of matter, creating denser regions and vast empty spaces. Over time, as the universe expanded, these fluctuations grew larger, shaping the large-scale structure of the cosmos we observe today. The Boötes Void, like other cosmic voids, has sparked intense curiosity among scientists, who continue to develop theories to explain its existence and the secrets it might hold. One widely discussed idea about its origin is that it formed through the merging of smaller voids. In the early universe, matter was distributed unevenly, creating denser regions where galaxies formed and less dense regions that eventually grew into voids. Over billions of years, these voids may have combined into larger ones, such as the Boötes Void. The arrangement of galaxies within it, forming a loose, tubular structure, supports this theory, suggesting that smaller voids coalesced to create this massive, near-empty expanse. A deeper understanding of voids like Boötes also ties back to the early moments of the universe. After the Big Bang, the cosmos was not uniform, but filled with tiny fluctuations in the density of matter, driven by quantum effects. These fluctuations caused some regions to become denser, pulling in more matter due to gravity. Less dense regions, meanwhile, were left increasingly empty as matter was drawn away. This process eventually led to the formation of the cosmic web, with galaxies clustering along dense filaments and vast empty spaces forming between them. Voids, therefore, serve as a window into the conditions and forces at play during the earliest stages of the universe. An essential part of studying voids is understanding the role of dark matter and dark energy. Dark matter, an invisible substance that interacts with regular matter through gravity, plays a key role in forming the large-scale structure of the universe. It helps hold galaxies and galaxy clusters together and shapes the cosmic web. However, voids are not just influenced by the absence of dark matter. They're also affected by dark energy. Dark energy, which drives the accelerated expansion of the universe, permeates voids just as it does other regions of space. Scientists believe that the presence of dark energy within voids allows them to grow larger over time, as it pushes galaxies and matter farther apart. This interplay between dark matter, dark energy, and regular matter is critical to understanding the evolution of the cosmos. The significance of studying voids extends beyond understanding their structure. These vast, empty regions provide valuable clues about the universe's early moments and its overall composition. By examining voids, astronomers can better understand how the cosmic web formed and evolved. Advanced imaging technology, powerful telescopes, and simulations using supercomputers have revolutionized void research. Projects like the Dark Energy Survey have been instrumental in mapping the distribution of galaxies and voids, offering a clearer picture of the universe's large-scale structure. These efforts allow scientists to compare observations with theoretical models, shedding light on fundamental questions about the nature of dark energy and the forces shaping the cosmos. While the Boötes Void is among the most famous, it's far from the only void in the universe. Other notable examples include the Eridanus supervoid, which is another large and puzzling void. This supervoid is one of the largest structures in the universe, stretching across about 1 billion light-years of space. Despite its immense size, it's not as completely empty as the Boötes Void. There are still galaxies scattered across the Eridanus supervoid, but there are far fewer than you would expect in such a vast region. What makes this void even more interesting is its connection to a phenomenon in the cosmic microwave background. the leftover radiation from the Big Bang. This radiation is usually evenly spread throughout the universe, but in the region of the Eridanus supervoid, scientists have noticed a cold spot that's a patch of space that is colder than expected. Some believe this cold spot might be caused by the Eridanus supervoid itself. As light from distant galaxies passes through the void, it loses some of its energy, causing this cold spot in the cosmic radiation. This is an example of a phenomenon known as the Sachs-Wolf effect, where voids can affect the cosmic background radiation. Another giant void, the Hound Dog supervoid, is located in the constellation Canis Venatici, which translates to the hunting dogs. This void is even larger than the Eridanus supervoid, measuring about 1.2 billion light-years across. Like the other supervoids, the Hound Dog supervoid is an area where galaxies are strangely sparse. It's a huge, empty region in an otherwise galaxy-filled universe. Scientists are still trying to understand how such a large and empty space could have formed. Was it caused by early cosmic inflation, dark energy, or something else? The mystery surrounding the Hound Dog supervoid is just one example of how the study of voids can help astronomers refine their models of the universe's development and structure. Researchers now are particularly interested in how cosmic voids relate to dark energy and the universe's expansion. In fact, some scientists propose that the very existence and expansion of these voids could be driving this acceleration, rather than an unknown energy source. This idea suggests that as voids grow, they exert pressure on the surrounding structures, contributing to the universe's rapid expansion. Moreover, voids may act as time capsules that preserve information about the early universe. Since these regions lack significant activity, they offer a pristine view of the cosmos in its earliest stages. Future studies of voids could provide crucial data to refine our understanding of cosmic processes, helping to answer long-standing questions about the origins and fate of the universe. What are your thoughts on it? Let us know in the comments below. And if you're interested to know more mysteries, watch our video on Do We Live Inside Someone's Mind? See you again. Bye.